Welcome to this video. In here we're going to talk about tree diagrams and complement rule. The complement of an event is a set of all outcomes that are not the event. So for example, if you've been asked to find the probability of A, you can use 1 minus probability of not A to find probability of A. And opposite with that calculation, probability of A plus probability of not A should equal to 1. There's several notations you can write. Probability of A plus probability of A prime equal to 1. Also A sub C, A like with a squeezy line, A with a bar on the top. So I usually use this notation right here. But those are all synonyms to each other. Those are all means not A. This is frequently rewritten to solve for the complement of A as follows. The complement rule. Probability of not A is equal to 1 minus probability of A. The complement rule can be very useful for at least one probability problems. This is because the complement of at least one is none, and sometimes it is very difficult to calculate all the possible ways that at least one may occur, but it is fairly straightforward to calculate how none occurs. So if the question have terms like at least one, that's a hint for you to use complement rule. So let's do it in practice. Roll 5 dice. What is the probability of at least 1 6 is showing? So if you want to use like the simple addition rule, you can see that you have to adding a lot of terms, which is pretty tedious. Well, the simpler way will be 1 minus 5 out of 6 to the 5th power. And how do I get this quantity right here? Because think about that. You're gonna, because we don't want to have 6, therefore we only left 5 sample space. And each one, we also don't want to row 6. Therefore, for each sample space, it has a probability of 5 over 6 to get at least 1 6 is showing. No 6 is showing. Therefore, you multiply them all together. Another way is to raise everything to the 5th power. You use 1 minus this quantity. It will give you the probability of at least 1 6 is showing. And this is the probability of not of no 6 is showing. Okay. So moving on, take a look at this example. A bomb in a plane's bomb bay is protected by 3 independent fail-safe switches. Each switch has a 0.99 probability of working correctly when the plane encounters extreme turbulence. If at least one switch works correctly, the bomb will not denotate. Suppose the plane encounters extreme turbulence. What is the probability that at least one switch works correctly? So we have three switches, and each switch has 0.99 probability of working correctly, and we want to know at least one switch works correctly. Therefore, we can first calculate the probability of no switch is working correctly, and that will be 0.01 for each. Since we have 3 switches, we're gonna times 3, not times 3, but times itself 3 times, which is raised to the 3rd power. This is the probability of no switch is working. We use 1 minus this probability. It will give you the probability of at least one switch works correctly. Finally, let's see how a probability tree can be very useful for solving complex probability problems that may provide multiple condition probabilities and ask you to solve for a 3rd probability, even sometimes another conditional probability. The formulas can be daunting in this case, so let's see what a tree can do for us. Take a look at this example. A certain disease is present in 0.005 of the population. A new blood test has been developed to test for the disease. If you have the disease, the blood test is accurate 98% of the time. If you don't have the disease, the test is accurate 97.2% of the time. Find the probability you have the disease given you've tested positive. So it seems like we have 2 conditions to met. And it may get very confusing if we're trying to approach this using formula. So a good way to do it is to use tree diagrams. So first of all, the certain disease, it's present 0.005 in the population. So 0.005 people in the population will have the disease, and 1 minus that value will give you 0.995 people who don't have disease. And from the people who have disease, the blood test is accurate 98% of the time. So it will be correctly identified positive 98% of the time, and will incorrectly identify as negative 0.02 or 2% of the time. For the people who don't have disease, the test is accurate 97.2% of the time, meaning 0.972 of the probability for people who don't have disease will be correctly testing negative. And for people who will be incorrectly testing positive will be 0.028, which is 1 minus 0.972. So in here, it kind of, it's getting confusing since negative and positive and correct and incorrect are switching like all the way. So it's very important for you to identify which is which and which should we really focus on. And the question is asking for the probability to have the disease given you've tested positive. So for testing positive, we're really going to focus on this branch and this branch. And but we only want to find the probability of actually have the disease. So it's only 0.98 right here. But don't forget to multiply by 0.005. So here's a little trick for you whenever you're doing with these problems, is multiply everything in the same branch. If 0.005 and 0.98 are in the same branch, then multiply them together. And same thing as the branch below. So what we're going to do is multiply these two together, divided by the probability of getting positive, testing positive. So testing positive, we have two branches, therefore we have to add them together to get the total probability. And doing some algebras or like mathematical ways, you will get the answer as 0.1496. Okay. Therefore, we can say the probability of testing the probability of have disease testing positive is 0.1496. Another way is testing having disease given you're testing positive. So, yep. And this is just a little tip. Go across means multiply. Multiple branches, you add them together. Okay. So that's all for this video. Thank you so much for watching. I hope you learned something from it. Thank you.